Yeah, we've heard Tobias Fitz talk this morning about gleichstellen Sätze, which is also highly related to work of Strassen. And now we're going to listen to Robert Robere. He's going to talk about a different version of this kind of dualities applied to the circuit complexity something. So that's a completely different kind of area. Not pure math, but like a circuit complexity application. So the title is Amortized Circuit Complexity, Formal Complexity Measures and Catalytic Algorithms. And Robert Robere, the stage is yours.
Thanks. So thanks for inviting me to speak. So this is joint work with Jeroen, actually. So the very beginning of this talk is going to be like a lot of review for most people in this workshop, probably. But then we'll learn some things that might be different. So the main focus of this kind of work is the idea of in computer science, what we would call a direct sum problem. And the basic idea of a direct sum problem is pretty simple. So if we have some computational task that we're trying to perform, right? Just think of some standard like decision problem, and we're given now n copies of it, like n instances of it. There's a very basic question you can ask. If I want to solve it, what's the most efficient way? Can I either run the fastest algorithm for one instance n times, or is there some way to get some sort of economy of scale and then like combine the computations together and then do better on average per copy, right? Very, very simple, basic question in computer science. And you can kind of formalize this if you don't look too closely at the notation anyway, it's like the following, right? So, if we imagine the cost of performing the task once, if we instead look at the cost of performing like n copies of the task together, sort of inside the cost divided by n, can this ever be like strictly below the cost of just performing the task like n times, say, achieving this kind of economy of scale idea? And one of the things is that these kinds of problems occur everywhere in theoretical computer science and beyond. Okay? So the classical example, which I sort of talked about earlier, actually, is the Shannon source coding theorem, which is the following, just so that everyone remembers. So, we have a one-way communication channel between two people, Alice and Bob, and Alice wants to send Bob a message, and her message is drawn from some distribution, right? There's some distribution of messages that she can draw from, and she wants to send the thing to Bob. And we imagine this happening many, many times. And the idea is that Alice wants to somehow pick a code for her messages so that on average, she sends as few bits as possible. And so this is inherently like an amortized kind of question, right? Like we can talk about the best one-shot code, but what Shannon proved back in the 40s now is that if we consider the amortized cost of like sending many, many, many copies of this in expectation, you can actually characterize what this amortized communication cost is going to be of the best possible code. And it's exactly the entropy of the message, right? And of course, we also know that we can basically achieve this in one shot using, standard coding tricks, right? What might be less known is that there's actually an extension of this to two-way communication. So let me just sort of briefly remind everyone of what the two-way communication model is. This is like pretty commonly studied in computer science, but maybe not outside. So in the two-way communication model, we have Alice and Bob again. And there's a fixed function that they want to compute. I don't know if this is going to work. Okay. There's a fixed function that they want to compute on a bipartite input domain. Okay. So we imagine that Alice gets one side of the input, Bob gets the other side of the input, and they also have access to some shared random bits, which they can use to help their computation. It's like a randomized algorithm. And then they both are unlimited computational power. The only thing that's restricting them from just computing the function and outputting it is the fact that they don't only see part of the input together, right? So what they want to do is they want to communicate some bits back and forth, and then, to try and learn information about each other's inputs and learn enough information so that eventually they can actually output the value of the function. Does that make sense? So, the thing we're trying to minimize here is the number of bits that we're going to communicate, say in the worst case. Okay? And of course, we can amortize this in the natural way, right? Now instead of just getting one copy of an input, Alice and Bob get n copies of their inputs. And now they want to output, any copies of the output. You want to compute, all of these copies somehow together while minimizing the number of bits communicated. And it's natural to ask, okay, well, is there a way to somehow, should we just run the protocol for one input n times, or should we somehow amortize, right? And the surprising fact is that the amortized communication is actually a smaller value than a single shot, just doing a single shot n times. So it's characterized by Mark Braverman and Anoop Rao, and it's exactly what's called the information complexity. And this is the mutual information between the inputs and the transcript of a protocol, basically. So this is also an information theoretic quantity. It can be less than the communication complexity. In fact, it can be exponentially separated from the one-shot communication complexity. So this is a very different situation from the Shannon situation, where over a one-way channel, you can basically do the same amortized versus not. Here, there's actually a massive separation between the information theoretic setting and the communication setting. And sometimes, so these are two very direct examples of these kind of direct sum problems, but sometimes we can study them without even realizing it. And one that's going to be very familiar to everyone in this workshop is the example of matrix multiplication, right? So, the matrix multiplication problem is, what's the smallest omega such that two n by n matrices can be multiplied using n to the omega operations. And we know that omega is at least 2 because you have to read all the inputs, right? And the best known upper bound is 2.372 something due to Ullman and Williams. And this, on the face of it, has no direct sum flavor, except for the fact that it's exactly the asymptotic tensor rank of some tensor, right? Some fixed particular tensor. So what's asymptotic tensor rank? Again, this is mostly review for this workshop, but the asymptotic tensor rank has the exact same flavor as this kind of direct sum problem that I wrote down a while ago. You take the m-fold tensor product and then take the mth root, and then you just take the limit as m tends to infinity. And we have this nice theorem which says there is a fixed 3 tensor, which is denoted by this 222, such that the asymptotic tensor rank is exactly 2 to the omega, right? So all you have to do is all you have to do is understand how asymptotic tensor rank can be different from tensor rank in order to characterize matrix multiplication algorithms. And this is actually constructive. Like, you can go from high power tensors to matrix multiplication algorithms, right? So there's a very interesting space thing going on here. So as has been said many times over this workshop, and in particular in Tobias's talk, so there's this beautiful theory of Strassen duality, which can be used to sort of characterize what these amortized values are. So I'll write it down I'll just write it down for matrices and just say the analogous conditionals for tensors. So for matrices A and B, I'm going to write A is less than T for tensor B if there are two matrices U and V such that A is equal to UBV, right? This is basically a rank inequality. So this is true if and only if the rank of A is at most the rank of B, right? And for tensors A and B, we write this if the analogous condition holds. So you need to take, for 3 tensors, you need to have 3, dimension 1 things and multiply on all the legs, right?
Sorry, just an additional.
Yep.
So what T means in this?
T means tensor for the tensor ordering.
T's a label.
Yeah, T's a label. It's nothing. It's the letter T. Yeah, just stands for tensor. And so in Strassen duality, right? We look at this forms a pre-order on the space of matrices or the space of tensors if you're going there. And then so we can consider this family of monotones on this pre-order. So this is the collection of all functions mu from tensors to non-negative numbers, such that mu, first of all, behaves nicely with respect to the matrices or tensors that we're dealing with. So it's additive under the direct sum, it's multiplicative under the tensor product. It's monotone with respect to the ordering. And then finally, it's normalized so that all the diagonal tensors, it takes the value you would expect it to, it takes value n, right? And then Strassen's theory basically says, well, you can characterize this asymptotic tensor rank exactly by taking the maximum value of the mu's over this family of tensors, right? So this family of mu's characterizes asymptotic tensor rank in this. So again, to calculate the matrix multiplication exponent, all we need to do now, with the knowledge of this nice theorem, is understand, this space of monotone functionals, right? Again, definite square quotes on the only, right? This is a really scary space to work with, but I mean, it does give you something, right? And Strassen general theory has been used to understand like quite a few things in previous years, like Jeroen's work on Shannon capacity, things like sunflowers and cap sets, quantum entanglement, and the list kind of just goes on. So now would be a good time to tell you the origin of this talk, like why I'm speaking at this workshop. So I have to bring us back to 2020, where Jeroen and I were doing our postdocs at the Institute for Advanced Study. And when you're doing your first postdoc there, everyone has to give a 2-hour talk on what they do. So Jeroen was giving his 2-hour talk on what he does, which was this stuff. And meanwhile, I was sitting in the audience. And the whole time that Jeroen was giving his talk, the only thing that I could think is that wow, these things are just formal complexity measures. And so I'm going to explain what that means. Okay, so I don't come from this algebraic complexity kind of background. I come from a circuit complexity and complexity theory background. So let's do a crash course on circuit complexity. So a Boolean formula is a tree-like Boolean circuit. Okay, so what do I mean by that? So I have some Boolean function that I want to compute, and I want to compute it using and/ors and not gates, right? And I'm going to do it like a tree. So this is an example of a Boolean formula. Does that make sense? And one of the main open problems in complexity theory is to prove superpolynomial lower bounds on formula size for any explicit family of Boolean functions, right? For non-explicit families, we can do counting arguments, like just silly tricks like that. But for there's very simple canonical families, which we believe to be hard, and we cannot prove any decent lower bounds on them at all. The best lower bounds that we have are something like n cubed, right? And now, how can you do this? Well, in fact, we have a complete method for proving lower bounds against Boolean formula size. Like it's complete in the sense that if any lower bound holds, then there has to be a lower bound in this method. And what is that? Well, that's the formal complexity measures that I was just alluding to. So what's a formal complexity measure? Well, a formal complexity measure is a map. Okay, it takes a Boolean function as input, and it outputs a non-negative real number. It's going to be monotone with respect to and or in the following sense. If I take the and of two functions, then mu of the and is at most mu of f plus mu of g. And if I take the or of the Boolean functions, then mu of f or g is at most mu of f plus mu of g. And then finally, mu is normalized on literals. So what I mean by that, if I have a variable or its negation, then the value of mu is at most 1. So it's just a function like this. And it's not hard to prove just by induction over formulas that any function that satisfies this property is a lower bound on formula size, right? You just prove this by bottom-up induction over the family. And also, it's not hard to convince yourself that f itself is a formal complexity measure. Formula size is itself a formal complexity measure, right? If I have a Boolean formula that computes fng, then the size of that formula is no more than the size it took to compute f plus the size it computes g, because it's a tree, right? Same thing with the ors and the literals. So this is a complete method. And this is basically a folklore fact. For any function f, the formula size is the max mu f over all of the formal complexity measures. So this was my thought the whole time that Jeroen was giving his talk back when we were doing our postdocs. So you line these two things up, and then you say, okay, well, is this a coincidence? And of course, the answer turns out to be no, otherwise I wouldn't be giving a talk. Okay, so let me talk about our results now. So I'm going to introduce the notion of what I'm going to call amortized circuit complexity. And it's going to be in a very general sense, but I'll try and do it with some examples so that we can follow along. So I'm going to let G, so we saw a second ago, for Boolean formulas, we were trying to compute Boolean functions using this finite gate set, ands and ors and nots, right? So I'm going to let G be a very general thing. It's going to be a finite set of gates. And what I'm going to call a gate is an extraordinarily general thing. Basically, it's just a map from Boolean functions to Boolean functions, okay? And it's a very general map. It doesn't even need to be fully defined in the space of Boolean functions. It just takes some input functions and outputs some functions. I can have non-uniform costs. I don't have to pay one for every gate or whatever. And then if I have this finite gate set, I'll let C sub G be the set of circuits that you can kind of build by composing these gates together. Maybe to keep something in mind, a good example of one of these things would be something called a branching program. So what's a branching program? Well, it's a way of computing Boolean functions like so it looks like this. It looks like a directed graph. And the vertices of the directed graph are labeled with Boolean variables. Okay. And on every single input, every single node is going to have two outgoing edges, one that corresponds to when the input is 1 and one that corresponds to when the input is 0. And given an assignment x, we just basically like activate all of the edges which are consistent, right? And then there's going to be a path going from the source node to some sink node, right? And so we label the two sink nodes 1 and 0, and that's going to be like, that's what we output, either 1 or 0. Does that make sense? So on this input, this branching program would output 1, right? 0, 1, 0, it outputs 1. So we would accept because it's a 1. And could anyone guess what the function what function this computes? When does this output 1? Parity, probably. Yeah, exactly. So this computes the XOR of the 3 bits, right? It outputs 1 if an odd number of the input bits are 1. But you can think about these things more generally, right? Like if I have an object like this, I can just think about the sink nodes as computing the following functions. Like, 1, if this sink is reachable from some source node in my program, right? So in this case, this bottom thing here, this is going to output 1 if an odd number of the input bits are 1. This top guy here is going to output 1 if an even number of the input bits are 1, right? And I bring this up just because, there's no need to tie ourselves to only having single inputs and single outputs and things like that. We can, it's a whole wide world out there. We can do whatever we want. So this is a very graphical notation for defining a Boolean function, right? And I'd like to tie it back to this notion of a circuit. And in fact, it's not hard to convince yourself that a branching program really is a kind of circuit built out of gates. So how is it built out of gates? Well, it's built out of the following 2 gates. You have access to an OR, where you take F and G and you output F or G. And you have access to what I call a query gate, where you take a function and a variable and its negation, and then you output F and Xi, and you also output F and not Xi, right? And the idea is like, if I have a circuit built out of these kind of gates, this is equivalent to a branching program because I can kind of grow it step by step. So like if you like a picture, maybe this is my source node, so I can query X1, learn that it's 1 or 0. And then at one of these sinks, I could say query X2, and then it's 1 or 0. And then maybe I could take the OR of these 2 gates, so I could just like link them together into one supernode, right? So by like a simple inductive argument, you can argue that like these kinds of programs are exactly what you get if you build circuits out of these kinds of gates. Okay. So and notice that this is a very general notion of gate, right? So this query gate has a very specific type of input. It takes an F and a variable and a negation, and it outputs like an F and Xi and F and not Xi. You can't just apply it to whatever inputs you want. So in particular, we allow like filters on the input functions in some sense. We also allow like non-uniform costs. Typically, branching programs are measured by like the number of edges that are occurring in the graph. And so to measure that, what we would say is that, well, OR gates are free. I could always take 2 nodes and merge them together. But every time I pay for a query gate, that introduces 2 more edges into my program. So the cost for this is 2. Yep.
So the query gate, isn't this just a function of F and Xi?
Yeah, sure. I just wrote it like that to even if it's, I just wrote like that to make it clear that I need both, but like the filter on the input still holds, right? I can't just take F and G and output F and G. You know what I mean? It has to be an input variable. Does that make sense?
There's 2 different kinds of inputs. There's functions and there's variables.
Yeah, well, I mean, it could be any function you want. It's kind of in general, it's kind of my point. For these query gates, I'm restricting you to only allow one of the inputs to be a Boolean variable. Yeah. Any other questions before we keep going? Okay. Well, so now we've seen how to define a branching program with a single source, and now you can say, well, okay, well, now I can have multiple sources. There's nothing really stopping me. So in general, if I have This is a very general way of defining a branching program. If I have some multi-set of Boolean functions, and let's say I want to write down a branching program that computes like all of them at once, right? So what is that going to look like? Well, you can think about it like this. Now our branching program can have multiple sources if it wants, and it can have multiple sinks. And each of the sinks just corresponds to, you know, whatever, if there's a path from some source node that reaches that sink node on an input. So for example, if I evaluated this program on 0, 1, 0, you get these edges becoming active. And now both of these source nodes get to go to G, right? And so we would just output G. We would say, okay, G of X evaluates to 1 on this input, and F of X evaluates to 0. But on a different input, you know, both sink nodes could become active. So we would say both of these output 1 now. So we can see now that this is not just computing like F and not F. It's really computing a family of functions, right? Does that make sense?
What does the green arrow mean?
Oh, yeah, good. So green means it's when it's 1, and red means when it's 0.
So from every query, there's a green arrow and a red arrow.
Yeah.
And you activate.
Yeah, so you activate the one that's consistent with whatever the input bit is. And maybe just one more, you know, 0, 0. Now everything evaluates to 0. Now the sources have switched, right? Like before, the first source went to F and the second source went to G. Now the sources have switched. We still say they both evaluate to 1, right? The point is that we output 1 at that sink if there exists a path from some source to the sink, right? We don't care about counting. Okay, good. Okay, so this is a sort of general definition. So now once we have this idea of a multi-set, like we can talk about this multi-set computation now. Well, what I'll call the amortized circuit complexity is going to be the following. It's going to be, take the multi-set that has n copies of F, right? Measure the cost of the smallest circuit that computes all of those functions among its output, and then divide it by m, and then take the limit, right? This is measuring the amortized cost of computation. Okay. And note here that I'm really evaluating the function, all of these functions on the same input, which is kind of a funky thing. What this means is that it's only interesting when the models themselves cannot like just copy output bits. And that's actually true of branching programs. Like branching programs, there's no branching program that will take in a bit and then output 2 copies of the same bit. So as soon as your model is powerful enough to sustain this copying operation, this is like not an interesting measure. It's just trivial.
It's not consistent with the previous direct sum problems. Where
no.
You had different.
Where I had different. Absolutely right. Yeah, good. Great. It's not consistent. So before it was being evaluated on different inputs. Now it's being evaluated on the same input. And that's what's interesting. That's what's going to be interesting about the spectrums that we're going to introduce, because it turns out this is the right definition. Any other questions? Yeah.
Why is it interesting to consider a circuit model where you can't copy?
Branching programs are a circuit model that can't copy. And branching programs capture how much memory you need to evaluate a function. So they definitionally capture like the minimum amount of memory needed to evaluate a Boolean function. So branching programs are a very interesting model because they capture space complexity and yet they can't copy. Yeah. And there's other copy-free models. Boolean formulas are another example. Boolean formulas can't copy anything. They're trees, right? As soon as I evaluate a function, I can't fan it out. I have to just use it once. And then if I want it again, I got to recompute it, right? So there's lots of interesting models actually that turn out to be copy-free.
But what do you mean that it captures the memory? Like in most reasonable models, if you want me to compute the same thing on the same output several times, I don't need more memory to do that. I'll just do it once and tell you the output several times.
Right. You have to be. I think the answer to this question is going to make more sense as we get further along. Yeah. I don't want to get too caught in the weeds too early. Yeah, you're right that for one copy it's okay. Like if I consider the branching program that just computes one function once, like the size of that is going to be like the 2 to the space needed by a Turing machine. Okay. Any other questions about this so far? Good. All right. So let me tell you now the first result, which is this duality theorem. So once we have this notion of a circuit, I mean, we can easily generalize the notion of a complexity measure, right? So this is a very generic notion of a complexity measure. This is what I'll call a G complexity measure. And all it's going to say is, well, it's going to be at most 1 for every input variable. Intuitively, input variables, I have to pay 1 to use them. And then for every gate, if I had a gate that maps some list of input functions to some list of output functions, and I have to pay C in order to use that gate, well, then I have this inequality, like the sum. I kind of like to think of it backwards. Like if I have that from all the f of i's, I can produce the g of i's. And then I also have to pay C in order to do that. Okay. And then the first main theorem that we had is that actually these formal complexity measures, which had been introduced in the literature before, when we'd come to it, it turns out that they exactly capture this amortized circuit size with the funny definition that you're evaluating it on the same input. So this is why this is the right definition, which is kind of a funny thing that sort of fell out actually from the statement. So actually, these formal complexity measures, which have been floating around all the time, it turns out that they exactly capture this amortized circuit complexity, which is quite interesting, I think. And this is a very general statement, right? Like it holds for any imaginable gate set you could possibly come up with.
Which side of the equivalence
is surprising?
No, is the motivation. Looks.
Oh, which side is
a weird definition on both sides.
Weird definition on both sides. So this is interesting because the reason why these measures are interesting is because by the same inductive argument, once I have one of these measures, I can prove a lower bound on the size of the circuit family, right? So this tells you, well, okay, if I want to prove a lower bound on F in these G circuits.
So it's a barrier.
It's a barrier, exactly, yeah. So what this says is like, okay, I'm actually not proving lower bounds on circuit size. I'm proving lower bounds on amortized circuit size, right? And this is where the second result comes in, which is that it turns out that for some of these natural measures, these things are always small. So another example of these copy-free circuits, which I happen to really like, come from these submodular complexity measures. So this satisfies the form of what you could call the submodular law, like f and g plus f or g is less than f plus g, right? So
for f and g.
For all f and g, yeah, for all f and g, yeah. And so these were actually introduced by Robere, who proved that actually these measures are always small. They're always at most order n. And if you want to convert this into a circuit, you get what's called a comparator circuit. I mean, you just look at the law and you just think about what the gate should be. And a comparator circuit can basically, it is a gate which takes in two inputs and it takes their and or simultaneously and then outputs them. A simple way to think about it is sorting the bits, right? It gets in a 1 and a 0 and then it sorts them into increasing order, right? And these have been studied a lot in theoretical computer science because they're models of sorting networks. And it turns out that they're actually quite an interesting kind of object to study. So this right here is an example of a comparator circuit that computes this family of functions, all the possible thresholds, right? Okay, so by applying our duality theorem to this submodular complexity result, we immediately get this kind of surprising fact that even though by counting arguments, there exist functions which are hard for comparator circuits to compute, it's very easy to prove that there exist hard functions for comparator circuits. You can compute any function with amortized size linear by a comparator circuit, which is very funky. So somehow, if I just want to compute lots and lots and lots of copies of my function, I can combine these computations together in an almost maximally overlapping way, like in a way that the cost per copy is only going to be n, like the cost it takes to read all the inputs to the function. So this is a very surprising result, I think. So let me say that this thing by Robere was also implied by Petechen, whose work was kind of important for our work, because for what I'll talk about in a minute. And the second remark, which was my main motivation for actually considering these submodular measures in the first place, is that if you restrict yourselves to monotone Boolean functions, so by that I mean whenever x is less than y, like bitwise, then the value of the function can only increase, flip to 1. Well, every monotone Boolean function can be computed, my chalkboard, by a monotone comparator circuit. So that's one that doesn't have negations. So Yeah. So if I disallow you from proving, if I disallow you from using negations, you can still compute all the monotone Boolean functions. You can set up this exact same, spectrum idea. Like I can still set up this notion of a submodular complexity measure. I just remove this from the rule because now you can't use negative functions anymore, right? But in this case, it turns out that we actually can get exponential lower bounds. In fact, you can get the right lower bounds. You can get lower bounds up to strength like 2 to the n, like the right number that you would expect even in the exponent. So there's something very strange. So this came from a work that I did, a series of works that I did starting back in 2016. I knew that we could use these monotone submodular measures to get literally the best possible lower bounds for monotone computation that we know. And yet, as soon as I allow negations inside, all of a sudden it drops from the best possible to basically the worst possible. This is a very surprising fact. Somehow amortization doesn't help monotone computation, but it does help non-monotone computation.
What happens if you allow negations but don't demand that it is normalized on the literal?
Oh, yeah, that's a good question. I don't know. Yeah, I don't know. I haven't thought about that. It's a good question. Yeah, any other questions? Okay. So now, I mean, another thing that kind of falls out of this framework is kind of the notion of catalysts, which also people here are probably familiar with, right? So the way that I think about it is like this: if I have like a submodular measure, say like one we just saw, let's suppose that I could somehow use the laws of the submodular measure to prove this inequality, right? There's no way of knowing that I didn't actually prove this inequality and then cancel out the mu's from either side, right? And so what this means is that these submodular measures, they can't see these hidden catalyst functions, H, which might be like living and being helping us somehow, right? And this introduces the notion of catalytic circuit complexity, which is what I'm going to talk about next. And the idea of a catalytic circuit, oh, it didn't update. Oh, there we go. The idea of a catalytic circuit is actually very simple. So I've given it, you can define this in general for like any family of circuits, but I'm just going to do it for comparator circuits because we just saw it. So what I'll call a catalytic comparator circuit, it's a comparator circuit which it gets its normal input variables and it wants to compute some set of output functions, but it can also get, along with its inputs, some set of functions that it just gets for free, and it can use them inside its computation as much as it wants. And then the only prescription is that at the output, it has to output exactly the same set of catalysts at the end of the day. And again, this crucially uses the fact that comparator circuits also cannot copy bits, right? If they could copy bits, then they could just copy the catalyst and use it for free. So again, here we're really using this copy-free property. So you can define the catalytic G circuit complexity, just like we defined the G circuit complexity or the amortized complexity. So this is going to be like the size of the smallest circuit for which I can use some set of catalysts to help my computation. And as a byproduct of our duality theorem, we can actually characterize this too. So it turns out we prove our duality theorem in a very different way than, not a very different way, but a kind of simpler way than is needed by like Strassen duality, which needs, axiom of choice level, well, not axiom of choice level things. So fortunately, in our setting, we can get away with using LP duality, which means that it's all constructive. So we end up characterizing this by the solution to an LP. Turns out that this catalytic thing is characterized by the best integer solution to that same LP. So there's kind of an, if you know what this is, it's kind of an interesting LP op, IP op that's been going on. So now Pierre's in the audience, so I have to talk about catalytic space. So catalytic circuits are indeed similar to catalytic space. So what is catalytic space? Well, it's a very kind of novel notion of computation, I think. So if I have an algorithm, say a Turing machine, a catalytic space Turing machine is the following. Basically, the motivation is kind of like this. If I have an algorithm, you can imagine I have access to some like massive hard drive that I'm able to use for my computation. And like the hard drive has like some sensitive information on it that I want to keep. You know what I mean? Like I don't want to just like throw out the stuff that's on the hard drive. So what I'll call a catalytic algorithm is one that like it's allowed to use this massive hard drive for free, as long as it returns the hard drive to its original configuration at the end of the computation. Does that make sense? Right? So a very natural question is, does this thing help? And the surprising fact is the answer is yes, they actually help a lot. If I have a very weak space-bounded model, like something that's only allowed a logarithmic amount of space, but I give you access to this catalytic tape, you can compute things that we believe, are not computed by just log space machines by themselves. So somehow this catalytic tape can really, really help our computations.
So does the algorithm know what the initial configuration is, or?
Perfect. Exactly my next slide. So this is the difference between the two states, right? In the normal definition of catalytic space, this returning to its original configuration has to hold no matter what the initial configuration was. Whereas in the definition of catalytic circuits that kind of falls out from our proof, you get to choose what the set of catalysts is, and then you can output them again later, right? So this is a subtle difference, and so this new, and to be clear, our new duality theorem does not characterize this version. It characterizes this version, the one where it exists. This is what falls out of it, okay? And it's an open problem to actually properly relate this. I mean, Jeroen and I worked for like months to try and prove that they were the same somehow, but everything we tried just kind of didn't work. But I can say, and this is our final result, which is that even though it's not clear if these are kind of directly related to one another, we can still translate some results from this family into this family. And so this requires actually working with catalytic space, but it turns out to still be possible to do it. So let me define this, okay? So we saw the definition of a branching program earlier, which is one that outputs a set of functions at these sync nodes, right? So what I'm going to call a catalytic branching program, it's a branching program just like before, but now instead of allowing a start node end up at any sync node it wants, there's like a pairing property happening. So every start node is paired up with a corresponding pair of sync nodes, like an accept node and a reject node. And we want the start node to go directly to either that accept node or that reject node. All of the computation paths have to be paired up in this way. You can't, maybe if I can draw a picture. In the definition of a branching program I showed you a second ago, I could have start nodes that end up here on some input X, and then on different input Y, it could end up, up here. There's no correlation between the start nodes and the sync nodes. In a catalytic branching program, in the old definition, all of the start nodes are paired up with sync nodes. So on every single input, this is going to go either to this node or to this node, right? And this one is going to go either to this node or in this node. And in the middle, they can go all over the place, right? But what's important is that at the end of the computation, it ends up with this pairing property.
And they're disjoint.
And they're disjoint. Yeah, they're disjoint. Yeah. And it turns out that enforcing this pairing property is the same as saying, I'm not going to let you depend on the initial configuration of the tape. And so you could in principle prove that this is what we were trying to do. You could in principle prove that these things were the same if you could turn anything like this into one of these. And that's what we tried to do for a long time and couldn't figure out how to do it. It's a very interesting question. I think they could be the same. It wouldn't shock me somehow if they were the same. We were convinced that they were the same, but yeah, it's very strange somehow. But because of this close relationship between these two models, you can kind of see how closely related they are. This is kind of why we can still convert some results that we prove for this model into the results for this model. Okay. So let me say what this is. So Pierre and with Jeroen and Koski pose the following problem. Does this catalytic space model actually help non-uniform computation? So in other words, if I let m go to infinity and I measure the amortized size per copy, can this be smaller than the branching program size? And they conjectured no. And then Aaron came along and proved actually every function has a catalytic branching program with linear size per copy, with the caveat that you had to take an absolutely massive number of copies in order to do it, like exponential. something like 2 to the 2 to the n. And we know that some blowup had to happen, right? If linear size per copy is possible, by counting arguments, you can still get exponential lower bounds. So something has to happen. You have to take lots of copies somewhere. But this is an absolutely massive thing. And so it's a very natural question to wonder if you could shrink the number of copies you need. And this was the thing that we were able to get using our framework. So what we can show is we can shrink this 2 to the n to something that's much better, provided that the function is a little bit structured. So as long as the function has degree d, as say a polynomial over GF2, then we can shrink the number of copies needed to get this linear size per copy down to something like 2 to the n of the d, which is much better for, degree 4 GF2 polynomials, which are, some of them are still believed to be kind of hard for branching programs. And the way that we prove this is kind of novel, actually. So what we did is we actually first proved a similar result using just functionals and thinking about dualities. And then we thought, hey, okay, maybe we can actually like translate this over into a direct catalytic construction, and it turned out to be possible. And we heavily, the main trick, if you want to call it that we exploit here is symmetry at the end of the day. So that's a statement of the results. So I'm going to move on to the proof ideas, but maybe I can pause for questions if anyone has a question. Okay, cool. Okay, so for the first results, which was our duality theorem. So here's just a reminder of what the statement looks like. So how do we prove it? Well, I mean, we have the expert here on proving these kinds of theorems, but his tools are way too complicated for us. So we just use good old-fashioned LP duality. Maybe for me, not for Jeroen. So let me give the idea of like how you actually construct an LP to prove this. So I have this formal complexity measure. Let's just think about formulas for a second. So what I'm going to do is I'm going to think about this formal complexity measure as like a list of rules to construct a formula, right? And so what I'm going to do is I'm going to introduce a special thing, just a 1, which corresponds to like paying 1, okay? And I start with some multi-set of copies of 1. And then at every single stage of the computation, I'm going to kind of like, I can take my multi-set and sort of transform it into a new multi-set of functions, sort of step by step according to these rules. So in particular, if I have a set of the form A that contains F and G, well, then I could like replace it with a new set of the form A with F and G, right? Similarly, if I have F and G, I can replace it and learn F or G. And at any point in time, if I have a copy of 1, well, I can pay and get a boolean literal. So I like to think of them as deduction rules because I do a lot of kind of proof theory. That's how I sort of think about these things. And so one nice way to think about these things is to sort of think of it like from F and G deduce like F and G, right? So here's the rules again. So how do we turn a formula into like a deduction in this family of inequalities? Well, you just kind of work your way from the bottom up. So I'm going to start with enough copies of 1 for every variable in my formula. I'll start off by using this deduction rule here to get a copy of all of the variables that are occurring at the bottom of the circuit. And then I'll just work my way from bottom to top, right? So if I want to add in this AND gate, well, this set has x1 and x2 in it. So I can apply this rule and deduce that x1 and x2 are there, right? And then you can like continue. If I want to add in the OR gate, then I can pick the literals for that and add the OR in. And then, eventually after, working my way to the top, you end up with something that looks like this. And so the way that we should interpret this F is less than 6 is like, this is saying that the formula complexity for F is at most 6. And the same idea works for any kind of program, any kind of circuit family you want, right? There's nothing specific about formulas I used here, really, right? So now how do we prove this duality theorem? Well, if I have these mu's, and I take a multi-set, well, I'm going to just linearize it over the set by just like summing out over. Well, I can just interpret this family of inequalities up here as literally a linear program. Like it is a linear program. I've already written it down. It's an exponentially big one. And we destroyed NYU's server at some point trying to run this program. So you can write down this linear program. And then what we showed is that, well, if you take the dual, any dual LP solution gives you exactly an amortized circuit by using this kind of interpretation that I showed you a second ago. And if you take an integral solution to the dual, you actually get a catalytic circuit because you can't rule out the fact that these extra catalysts are floating around. So this is something that's kind of nice about this duality theorem, is that it's constructive. Like we can actually run the program. And we were actually able to find some interesting examples of these measures. Very small ones, but you know, because it's a 2 to the n size linear program. But yeah, you could still run it, which was interesting. So the duality theorem that I said earlier is kind of a simplification of what we can really prove. Like we can actually really just characterize any inequality that you want. If you pick any inequality that's true of these measures, you can actually fully characterize what that inequality means. And what it means is the following. So if I have any two multisets of functions such that this holds for all of the complexity measures, right? Well, what that means is that there's some set of catalysts and some positive integer k such that this inequality holds. And the way that you should think about this is it's like, if I have a circuit for k copies of A and T as input, then I can run the circuit and get T again and k copies of B. So it turns out that these inequalities just like sort of exactly characterize this kind of computation. And of course, I mean, again, to call back to this morning's talk, I mean, it's actually way more convenient to phrase this in the language of semigroups rather than circuits. Like these are just sort of specializations of everything. So I mean, what's the underlying algebraic structure that's happening here? Well, we have a semigroup, and the semigroup is the set of all multisets of n-bit Boolean functions, and plus is the disjoint union of multisets in this case. And then we have this, it's equipped with this preorder, which we think of as saying like, I can compute A from B using G gates, using some circuit of G gates in the middle. And it turns out to be more convenient and way more general to just prove this duality theorem. We still use LPs to do all this. And you know, it turns out to be way more general to just prove it this way. And so we do it once, and then you can easily specialize it to be a circuit family. And let me, something that probably some people have noticed is that this is something that's a simplification of this setting, is that we really don't have a multiplication here, right? We really only have addition. And this is fundamentally why we could use LPs in the first place, right? Like LPs don't play well with the multiplying two variables together.
It's really more about dimensionality, that your setting is finite dimensional versus and sort of finitely generated.
Finitely generated. Yeah, that's true too. Yeah.
Whereas for finitely presented semiring, I guess.
Yeah, that's true. Actually, yeah, for any finitely presented one, yeah, that's actually true. That's a good point. Yeah, sorry. Yeah, that's a better way of saying it. Thank you. Yeah. Good. Okay. So now let me say just a few in the last couple of minutes. Let me just say like a few very few comments on these bounds for catalytic space. I can't really say much about how we do this because this is kind of the most technical thing in the paper. So the basic idea is to start with a result using our duality theorem and then somehow implement this. Okay. So let me say what we do here. So the key tool that we use here is symmetry at the end of the day. And the idea is to go back to this paper by Razborov and look at how he proved that submodular measures must be at most order n for Boolean functions. Okay, so how did he do it? Well, if you break his proof down, it's not that complicated. It turns out to boil down to this very simple symmetry property. Okay, and it's the following: if I have two uniformly random functions on n bits, n minus 1 bits, sorry, and then I have a third uniformly random function on n bits, then the following three distributions are the same. I either sample a random function on n bits, or I sample two random functions on n minus 1 bits, and then take the DNF. Either if xn is 0 is 0, then I output this, and if it's 1, I output this, right? Or if I can take the clausal form of it, which is just the same thing. These are just three ways of expressing a uniformly random function on n bits. So this is a symmetry property, if you like, right? And so what we were thinking was that, okay, what if we explicitly enforce these symmetries inside of these inside these complexity measures? So let's say, just for variety, let's consider branching program complexity measures. So these are the rules that just come from the gates, but these kind of aren't important for this slide. What's important is this new symmetry property. So I'll say it's symmetric if mu of f is at most mu of f XOR I, where this is just like the function that you obtain by negating the ith bit. So whenever this is true, this is true. And so let me note that if we were just thinking about circuit complexity, like these two things are obviously like related to each other, right? If I interpreted this as literally being circuit complexity, then this is at most this, right? Because I could just negate the ith input bit. Like that would be a program that computes the same thing. In the branching program, you can just switch the outputs of all the xi gates inside of it, right? So our thinking was, well, we should just be able to explicitly enforce these symmetries and not change the complexity of the thing, right? Like they seem to preserve computation, like normal computation. So why not just explicitly enforce them? And you should think of this, where this symmetry is related to this symmetry is the fact that like when I go from the DNF form to the CNF form, you get that this negation flips spots. That was kind of somehow the intuition for where this came from. So what we showed actually is that if we assume the measure is symmetric, you can hugely improve the upper bound on the on Rasborov's upper bound. So not only do you get that mu of f is at most n, you actually get that it's a very, very small number. It's in fact, I'll say the definition and probably not very many people are going to know what it means, but that's fine. You take the decision tree that computes f with the minimum expected number of queries over the uniform distribution. And this is a funny thing because if I take something like and, this is a very, very small number, like it's only constant. So we were looking at this and we were like, wow, okay, if this is true, then we can hugely improve the rules for catalytic space, right? Like if this can somehow be translated back to the catalytic space setting, I mean, maybe we can somehow use this massive improvement and change 2 to the 2 to the n to like 2 to the order n, right? So are all measures symmetric? This was the idea we asked ourselves. No, and this is why you write computer programs. You can construct a counterexample. I mean, we didn't construct a counterexample, the computer did it. I don't even really think we ever really understood like why it worked. But it turns out that there are counterexamples to symmetric measures. However, that didn't stop us. So what we said instead, well, okay, instead of just worrying about the counterexample, we could just symmetrize, just like work over the orbit of everything, right? It turns out that that still works. So instead of so now for any branching program measure, not only symmetric, if you're satisfied with computing the orbit of f under the natural action by negating some of the input bits, you can still get this improved quantity on average, this d average instead of the just n on the right hand side, which is what was there before. And then finally, we need to use this result. So this is like, to be clear, this is like just some deduction that we do inside the laws of submodular, inside the laws of branching program complexity measures, right? Like this is like just some sort of abstract nonsense calculation that we did. Now what we have to do is we have to somehow convert that into a catalytic branching program. So we need to use it to somehow compute lots of copies of f. This turns out to be a little bit technical. So first we need to show that it's sufficient to compute the span of the orbit. And then we need to somehow implement all of this as a catalytic branching program. And I'm not going to worry about these kind of details. I'll just refer you to our paper if you want to have a look. Okay, and that's all that 3 o'clock, that's all I have time to say. So let me just say that this work suggests many open problems. So maybe I can just say, some of these things have already been talked about literally today. So entropy, yes, we can do it in some sense. So parallel repetition, something we were talking about over the break. So a very interesting question is whether or not we can express this information as amortized communication result that I said earlier, where you allow two-way communication as opposed to one-way communication. This seems like a very natural measure to study. It's a very natural amortized scenario. Should be some way to put it inside of this framework. Other obvious questions is to like further improve the upper bounds for catalytic space. So this was partially done by Cook and Mertz in 2022. Some relationships with different preorders, and also to actually understand what's going on with the original motivation for me, at least, which was this relationship between non-monotone computation and monotone computation. But yeah, that's it. That's all I have time for. So yeah, thanks.
Just Wi-Fi, someone who got kicked out in the.
Oh, that's why.
The last slide.
Okay.
Any questions?
Yeah.
What do you mean by expressing entropy on the last slide?
Oh, that's what you talked about this morning, right? Like, is there a pre-order that kind of where the Well, just like we did this morning with the majorization preorder, right? Like the functionals there are like the entropies, right? That's all that I meant. Yeah. And so this is kind of like since that's the one-way communication, it would be very interesting to understand the two-way communication version of that. That's the second point. The information is randomized communication.
But what's the final message if one is interested in branching program lower bounds?
Yeah, the final message is. Sorry, go ahead.
Is it just going to depress people?
I think this is just going to depress people, basically, is the answer. It was interesting because for formula measures, this exactly characterizes complexity because of tree-like. But I think it's like somehow a very surprising fact that you can really interleave these computations in a non-trivial way, right? Like the lesson of this, I think, is not. I don't think it's a negative one. I think it's a positive one, and that is that catalytic space. The idea of catalytic space is a much more powerful thing than you think, right? And it's already been used to like improve upper bounds for some log space problems like tree evaluation and things like that. So yeah, but for lower bounds, I mean, this gives an exact characterization and just proves that actually no, this surprising catalytic upper bound just completely rules out this approach to proving lower bounds.
But you need the exponential.
Yeah,
so if you're restricted to polynomially or exponentially many repetitions, could you get some depressing results?
That's a good question. Yeah, that's a very good question. I mean, like if you restrict your M to be below the threshold where counting arguments kill you, you can still hope to prove something. Yeah, you could absolutely do that. Yeah. It's also kind of an interesting question about, something that I would really like to understand in this space is the role of these catalysts, actually, because it seems like maybe, I'm wondering if catalysts are kind of actually the problem and not the actual functions themselves. Like, I don't know, I have this kind of feeling that maybe you can somehow eliminate this many copies thing entirely and still get this result. But the trade-off is that you would somehow get some huge family of catalysts that you have to like use and then compute instead along the way, right? That seems very plausible to me that could actually be true. Yeah, I'd probably talk about it offline. Yeah.